Okay. So pi, remember what it means. It means that there exists a sequence Sn, Pn, so that
Oh, there's someone online.
Ti, Ti Sj is delta Ij for every I. So what we know is that if E is SPI, then LE is pi. But for example, this graph uh, the Leavitt path algebra of this graph is pi, but this is not simple. It's not simple, or is it simple? Well, there is some graph. So that this is C of this. C is the cone algebra. The cone algebra of a graph is the Leavitt path algebra of some other graph. And the cone algebra is never simple because by definition you omit a relation when you define it, and that relation gives you an ideal, an non-trivial ideal. So this one is pi, but not simple. Yeah. This one I haven't mentioned before. Yeah. 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 One maximal, one ideal that is maximal among two-sided ones.
Yeah, right. So,
Yeah. So you have others, like, what was it? They characterize E so that stable finitely generated projective, or stable free finitely generated projective modules are free. This was one, and what was the other? There was you had two about stably free.
stably free, yeah. And the other one was any projective module is stably free.
Such that any finitely generated projective is stably free. What else? Well, you have, I mean, going out of Leavitt and into K, what happens if you take K0, 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 K0 of some commutative ring L? And I also asked, say, if K0 of LE star for L equals C in, so the map from here to here is an isomorphism. This was the group completion of equivalence classes of self-adjoint idempotent matrices modulo unitary equivalence. Okay, so that's what the star stands for. Whether that is BFE. There is a canonical map, and the point is whether this is, it's always a split mono. Why? Because you can map this to K0 of LE, and this is BFE, and you can check that this is the identity map. So the point is whether this is onto, or there are more. And yeah. You want to, Gilles, do you want to explain the labeled thing? Well, yeah, well, of course, yeah. Yeah, well, but these are already in books, right? Yeah, which adds, so I have a negative result, but which still doesn't solve the problem. So, so recall L2 is L of this, and L2 minus is L of this. And the question is whether L2 is isomorphic to L2 minus. And, well, the theorem we have with Guido Arnone, which stoically attended all the lectures, says that there exists, so the following. So suppose you have the Leavitt path algebra, so this is C-graded, right? Now, any C-graded algebra is graded over any quotient of C, namely over every, so you can write this as follows. You fix M. And then you can do this. You can put together all the homogeneous components that are congruent modulo M. Okay? And this gives you a C mod MC grading. Okay? And what we prove is that there exists no homomorphism from L2 to L2 minus or L2 minus to L2 such that phi is C mod M homogeneous and sends 1 to 1. There are no maps. Not only there are no isomorphisms, no maps at all. No unital algebra homomorphisms for any M. Now, does this solve the problem of whether these are isomorphic? No. But if there is an isomorphism, it's the farthest thing removed from a homogeneous thing that you can imagine. But it was already known that there couldn't be an isomorphism that was C homogeneous, right? But it cannot be ZM homogeneous either for any M. And so it's also known that if you take the ground ring to be the integers, then there is no star isomorphism between L2 and L2 minus. And well, I mean, the results that I know of are all of the sort. There is no isomorphism that, in addition to being an isomorphism, satisfies this additional property. Okay, so they are all negative, but none of them disproves the possible existence of an isomorphism. In the case when the ground ring is the complex number, say, which is the main case of interest. Yeah.
Really, just one question. So ESPI implies PI. Why is that?
Oh, well, this is in my paper, but well, you know this. Yeah. So I have to recall the proof. Well, of course, over a field, LE is simple purely infinite, and any simple purely infinite ring is properly infinite, and this is already in the Ara Goodell Pardo paper where they study the K0 purely infinite simple rings. But I say that this is true even when the ground ring is not a field, and this is using the graphic argument, which I do not recall. So to be in PI, what it means is that there is an isomorphism from a homomorphism from C infinity to R. This is what it means for R to be PI, because C infinity is the ring defined by two sets of generators, Sn and Tn, that satisfy these relations. Right? And this in particular has a map from C2, which is the same, but the sequences end at 2. And this also maps to C2. So if you have a homomorphism from C infinity to R, you have one from C2. And if you have one from C2, you have a homomorphism from C infinity. Right? So what you need is to find an S1, T1, S2, T2 that satisfy these relations. And this you build at hand using the hypothesis on the graph. So I was asking Gilles if he wanted to. You want to come up, or you want to say?
Just before that, this isomorphism, I was talking to Roosevelt that isomorphism between L2 and L2 minus, is it known that it cannot preserve diagonal?
I think so, yes.
Yeah.
Yeah, because I think that the proof, yeah, I think that Toke had, and somebody else had proven that there is no isomorphism that preserves the diagonal. And actually, the proof that there is no star homomorphism in the case when the ground is the integers due to Sorensen and somebody else consists of showing that any such homomorphism would necessarily map the diagonal to the diagonal. And hence it wouldn't exist. Yeah.
We're just thinking that maybe we're taking pictures so that we know the problems. No, no, but yeah. So my question is about this left label path algebra that I defined in my talk last week. And so I've given an example of a left label path algebra which is not isomorphic to any left path algebra. So as far as isomorphism goes, this class of algebras is strictly larger. But there's another thing that we can try to look at, it's Morita equivalence. So maybe try to find an example. Well, so that's for labeled, the second L. So an example of a left labeled path algebra that's not Morita equivalent. To any left path algebra. Huh? So then I'll talk about this week about ultragraphs. So there is the notion of it's a little bit more general than graphs. So we have the left path algebras for ultragraphs. So this is kind of in the middle. So every algebra like this is every algebra of an ultrograph is a path algebra. But on the other hand, we also shown that as far as isomorphism go, this class is still bigger. And there's a thesis that shows that for ultragraphs, left path algebra for ultragraphs are always Morita equivalents to some left path algebra graph. So as far as Morita equivalents go, ultragraphs does not give anything new. If you try to look for these labeled path algebras, maybe we have something different as far as Morita equivalence goes. And another thing that I was just thinking, for sister algebra, this is known, but the problem is I'm not sure if the proof is going to be easy to adapt to the pre-algebraic case because they use the operator theory in the proofs. But it's possible that the same example that works there, it works here as well. But there's another problem in these isomorphic goals is that I think that is still open if for two graphs. Say E and F graphs. It's kind of the isomorph problem, but it's the Morita equivalence problem. So is the sister algebra of E Morita equivalent to the sister algebra of F? This is also bad, but if and only if the left path algebra of E, let's say over the field C, is Morita equivalent to left path algebra of F. This is something that I think it's also not known. I'm not sure. Maybe one direction is okay, but I don't know. And if you look to Mark Tomford's website, he has a page of open problems in this graph algebras. So I guess you can try to look at his web page. I'm not sure if it's up to date there, but at least you can try to look and maybe ask him if it's something that's still open. Which includes, I think, these isomorphisms and some of the open problems that Leah told us about last week. So Leah, so in the end of her mini course, she gives several also open problems. There's a lot of stuff to be done.
I don't know. So, yeah, Mark Tomford's webpage. Now he's back in Colorado. No, in Bristol Boulder, right? I think. No, Colorado Springs. So he's also writing, I think, a book. There's no math. So he has a column where he does articles and things. So it's interesting webpage to visit. It's not only the graph algebra open problem list. Okay, so if not, I think that was it for today. We'll end now.